Hey everybody, this is our video solution to problem 8a from Superquiz 2. This is one of two problems on the exam where we're actually getting to do what we want to do, which is solve differential equations. So here we're given an initial value problem. It's a second order differential equation. The forcing function is 2 cosine of t, and we're given these initial values. Y at 0 is 1 and y prime of 0 is 0. And the idea is, hey, we're going to try to solve this by using the Laplace transform. All right, well, let's give it a try. So we're going to apply the Laplace transform to both sides of this differential equation. So when I apply it to y double prime, I'm going to get s squared ly minus s times y of 0 minus y prime of 0. Okay, so this is just our rule for computing the Laplace transform of a second derivative. Okay, then I need to do minus 4 times the Laplace transform of y prime. So minus 4 times, okay, the Laplace transform of y prime is s ly minus y of 0. And then finally, I'll have 5 times the Laplace transform of y. Okay, what about the right-hand side? Well, I have 2 times, I need the Laplace transform of cosine of t. That's s over s squared plus 1, right? Maybe I'll move the 2 into the numerator. That's fine. All right, let's do a little rearranging and solve for y, or solve for ly. So let's see. So how many ly's do I have? I have s squared, and I have minus 4s, and plus 5. All right, but there's some other junk, and let's see what that is. So first, y of 0, there's our initial value. Y of 0 is equal to 1. So I have minus s, and then minus y prime. Ooh, but y prime is 0. Hey, that's nice. Okay, then I also have minus 4 times minus, this is 1, so that'll be plus 4. Okay, and this is still equal to 2s over s squared plus 1. So I'm going to add these to both sides and then divide by this quadratic. So I'm going to add s minus 4, and I'll divide then by s squared minus 4s plus 5. And that gives me ly equals, so let's see, I have s minus 4 plus 2s over s squared plus 1. And then I need to divide everything by this s squared minus 4s plus 5. Okay, well, we might be able to put this together a little bit. So first thing, this is a sum, so I could actually, if I wanted, I could split it into 2 pieces, right? Maybe that wouldn't be so bad. Or I could just toss this all together. Oh, maybe that. Like, okay, so what happens if I toss everything together? So first I'll combine these fractions. So let's see, I'm going to get, oh boy, a cube. I don't want a cube, man. Cubic sounds really bad. Okay, let me split it up. So I'm going to do s minus 4 over s squared minus 4s plus 5, plus, then I'll have 2s over s squared plus 1 and s squared minus 4s plus 5. Okay, so this first one, I think I'm probably going to want to complete this square here. So I get s minus 2 quantity squared. And let's see, that would give me a 4, but I have a 5, so I need to put a plus 1. All right, and well, this is that same sort of situation we had in the previous problem. I'm going to want to break this up. Now there's a shift in here of minus 2, so maybe I'll, instead of writing a minus 4, I'll write a minus 2. And of course that's a little bit of cheating here, so I'll write another minus 2. So this piece I can break up as s minus 2 over s minus 2 squared plus 1. And then I'll have minus 2 times 1 over s minus 2 squared plus 1. And the reason I'm really happy about this is I can just see right from the table. by the first shifting theorem. This is going to be the Laplace transform of the cosine of t times e to the 2t. And this bit here is the Laplace transform of sine of 2t times e to the 2t. Cool. Now we got to deal with this other bit. Right. So this other bit, that looks like, yeah, partial fractions. And oh, how gross, right? There's two quadratics. Now, maybe does this factor? Let's see. You take -4 and square it, and you subtract 4 times 1 times 5. That's 16 minus 20. Oop, that's negative. Nope. We're really going to have to do partial fractions with two irreducible quadratics. Oh, man. Dr. Glesser, you really are a jerk. Okay. Let's see here. So I have 2s over s squared plus 1 times s squared minus 4s plus 5. And I want to break this up as something over s squared plus 1 and something over s squared minus 4s plus 5. Okay, what do the numerators have to look like? Well, because these are irreducible quadratics, they have to be linear pieces. Okay, let's clear the denominators. So we get 2s is equal to as plus b times s squared minus 4s plus 5. Okay, plus cs plus d times s squared plus 1. All right, well, I don't know that there's going to be any real simple way to do this, so let's just expand it. The highest power is going to be an s cubed. Let's start there. And let's see, I have no s cubes on the left. On the right, I'll get a times s squared. That's as cubed. And then c times s squared, so plus a c. Okay, well, I'm not going to have to worry about writing c anymore. C is negative a. All right, how about s squareds? There's no s squareds on the left, and on the right, okay, I could do as times negative 4s, so it's minus 4a. But I could also do b times s squared, so I get plus b. Let's see, I can't use the c, but I could use d times s squared, so plus a d. Okay, I don't see much to do at this point, so let's go on to the s. I have two s's on the left. On the right, I could do as times 5, so that's 5a. I could also do b times negative 4s, so it's minus 4b. Let's see, cs times 1, so it'll be plus a c. Ooh, but plus a c is the same thing as plus a negative a, so that's like a minus an a. So this is 4a minus 4b. I could solve for b here. Let's see. If I add 4b and subtract the 2, I get 4b equals 4a minus 2. And so b divided by 4, right? Divide by 4, and I get a minus 2 over 4, which is 1/2. Okay, so I've written so far c in terms of a and b in terms of a. If I could get d, that'd be pretty good. Let's look at the constants then. There's no constant on the left. On the right, let's see, I can't use a. I could do 5b. And I could do d times 1. Okay, but 5b, I know what b is. B is a minus 1/2, so this is 5a minus 5/2. And then we have plus d. Oh, cool, I can solve for d now. So d is going to equal negative 5a plus 5/2. All right, so I've now solved C, B, and D all in terms of A. I just need to know what A is. And what can I do? I have not used this S squared one. So let's rewrite this. I have negative 4A, negative 4A plus B. But B is A minus 1/2 plus D. D is minus 5A plus 5/2. Okay, let's combine that. I have negative 4A plus A, that's negative 3A. Minus 5a, so negative 8a. And then, let's see, 5/2 minus 1/2, that's 4/2, which is, 4/2 is 2. So, negative 8a plus 2 is equal to 0. So that tells me that a is equal to, let's see, we'll subtract 2 and then divide by negative 8. Oh, that's a fourth. Okay, so what do we have? We have A is equal to 1/4. B is A minus a half, so that's a fourth minus a half, that's negative a fourth. C is just the opposite of A, so that's also negative a fourth. And D, ooh, okay, negative 5 times A plus 5 halves. Well, okay, A is a fourth. So this is negative 5/4 plus 5 halves. Ah, okay, so that's 5 halves minus 5/4. That's what? That's just 5/4 again. Okay, so we can go back over here and rewrite this as 1/4 S minus a fourth. Ooh, that feels like I want to pull a fourth all the way out, doesn't it? Yeah, let's just do that. Let's pull a fourth to the front, and then we just have S minus 1. Ooh, that doesn't feel as bad. And then this C is negative 1/4, and this D is 5/4. Ooh, again, I really want to pull that fourth out. Let's just do that. In fact, let's even pull maybe a negative out, right? So I don't have to worry about things. So I have negative a fourth, right? So this was, now it's just an S. Now it becomes a minus 5, right? It was 5/4, but now it's just a 5. And it was a plus 5/4, right? But I pulled the minus out. Okay, this is actually not terrible because I can split these a little bit more. So I have a fourth, and what if I split this as S over S squared plus 1 minus 1 over S squared plus 1? These come right from the table. This is the Laplace transform of cosine of t, and this is the Laplace transform of sine of t. Hey, that's not too bad. Okay, well, let's see. Let's make these a little bit smaller. All right, now I need this bit, but let's see. I have minus a fourth, and again, I could break this up, and oh, this gross thing on the bottom, though. All right, we better do this trick. S minus 2 squared plus 1. Ah, so what I really want is an S minus 2 on top. Okay, well, S minus 5, I could just pretend that was S minus 2, and then minus 3. So I can break this up as S minus 2 over S minus 2 squared plus 1. And then I have minus 3, which I just pull out to the front there, this minus 3, and then I have 1 over S minus 2 squared plus 1. And again, this is easy to see from the table. This is the Laplace transform of cosine of t times e to the 2t. It's First Shifting Theorem. And this piece is the Laplace transform of sine of t times e to the 2t. Again, First Shifting Theorem. Okay, we can put this all together now. Whoa. Come on, OneNote. All right. So if I put this all together, then I've figured out all these are Laplace transforms. So let's take the inverse Laplace transform. What is my y? Okay, I had a cosine of t e to the 2t. And I feel like there were more of those somewhere. Let's see. So we have 1, 2, 3, 4, 5, 6 pieces. Okay, there we go. Look, there's one and there's one. Now this has a minus 1/4. I can't forget the minus 1/4. So I have one of them and then minus a fourth of them. So I have 3/4 cosine of t e to the 2t. Okay, so check and check. Okay, then I have a sine of 2t e to the 2t, and there's another one over here, and it looks like there are minus 2 and then plus 3/4. Minus 2, that's same as minus 8/4, and then plus 3/4, so that's going to be minus 5/4. So minus 5/4 sine of t e to the 2t. Okay, so those are done. And then what's left? I just have this fourth, well, these guys, let me just combine them, a fourth cosine of t minus sine of t. And there we go, we solve for y. Yeah, it's not short. There's a lot of work to be done here, right? That's partial fractions. What a pain. Okay, but we have the tools, right? We just have to keep our nose to the grindstone and suss it all out.